Okay, today we're talking about work and energy, and so we've talked so far about doing work as our work is our force times the distance. So work equals force times the distance times cosine theta for the distance between them. And we've talked about potential energy. Okay, which right now equals mgh, but that's really just the energy due to a position of something. So if we lift an object up to a particular height, and that height gives it this much potential energy. Well, here's the question: is what if we give something potential energy and then like push it off the ledge? Or so we lift a shot put off the ground and put it on the table, and then we roll it off the table and let it drop. What happens to that energy once it's no longer potential? Once it starts to do what we're afraid that something with potential energy might do. So here's our example. We're going to take this. This boulder right here, and this is a frictionless valley, right? So this boulder's on the edge of a hill, on the edge of a cliff, and if we give it a nudge, what is it going to do?
It's gonna fall.
It's going to roll down, right? Okay. So my first question is, if I roll it down, if I give it a nudge and it rolls down, what is it going to do after it's at the bottom? Does it stop here?
No, it's gonna try and go back up.
It's going to try and go back up, yeah. Okay, how high?
However high
Like
the
halfway.
speed will take it.
Like just to, so you say to about here?
Oh no, it's gonna stop like this and go back up.
It's going to stop here. Oh, and then roll back. Well, I mean, but the highest point it'll reach is about here?
No, a little bit more.
You say higher?
Up or down, right there.
Like, so at the same height, so Alex is saying at the same height that, I don't want that to drop from the middle. Oh well. So you're saying, pretty much the same height, right?
Yeah.
And you say no. Because why? Have a reason. Okay. Alex is right. That this, if this boulder that starts here should roll down, if there's no friction, nothing else acting on it, should roll down and get up to the same point up here. Okay. And here's why. If we're measuring our, if we are measuring our height, let's say we're measuring our height above this place right here, yeah? Then that's the total height difference between the top of the hill and the bottom, right? Is this h right here? Okay. So if we let it roll down, then our potential energy here, okay, should equal our potential energy here, because they have the same height. So if it rolls down, it should roll all the way back up to where it gets the same potential energy.
But eventually it'll stop right in the middle.
Well, if we make this frictionless and we assume that there's nothing acting on the boulder that's going to slow it down, then it should go like this forever. Okay, but it's not in the real world. But if in our make-believe world where everything's frictionless and doesn't have air resistance and have all these other things acting on it, in our imaginary physics world, it should do that. Okay, but it doesn't, and there's real things that happen. We do have friction. It would eventually, Elena, do what you said. Would go up to about here, and then roll down about to here, and to there, and eventually do this. Yeah. Okay, but that's real world. Okay, we know it's going to happen. The math is a little harder on that. Okay, but in the perfect world and in the physics intention of physics world, it'll go all the way back up. Okay, now here's my question. What is it like when it's down here? After the first roll. When it first rolls down, what's going on? What is it like when it's down here? What is its potential energy? Potential energy equals what? Equals 0, right? Because its height is gone. It lost all of its height for its potential energy, right? So where did it go? Well, I haven't told you this yet. There's another kind of energy, and it is called kinetic energy. Okay, and kinetic energy is the energy an object has due to motion. If an object is moving, it has kinetic energy. If it's spinning, it has kinetic energy. Any kind of motion gives something kinetic energy. Okay, the general formula for it is,
Wait, what is that face for?
this is kind of ugly in here, but this is energy due to motion. All right, and the formula for it, kinetic energy equals 1/2 the mass of the object times its velocity, its speed squared. However fast it's going, squared. Now, velocity doesn't matter. Okay, in other words, direction doesn't matter. It's just how fast it's going. Because if it's energy due to motion, then the least amount of kinetic energy you can have is not moving, right? Which means your speed would be 0. That make sense? Okay. So, if up here we have
Haven't we used something like that already? As of light? Formula light?
not quite, I don't think. Down here, up here we have a potential energy of mgh, but our ball isn't moving, or our boulder. Okay. Down here at the bottom, where potential energy equals 0, our kinetic energy equals 1/2 mv squared. All of our potential energy becomes kinetic energy. And then, when we roll back up again, our potential energy again equals mgh, but our kinetic equals 0 again. All right. So what happens is this, our boulder here goes from all of it being potential to all of it kinetic to all of it potential and back and forth. That's not what I meant to do.
You can move the words too.
Yeah. Okay, so you follow here? All right, so that means that we have something called our total mechanical energy. Okay, and there's two ways we're going to see it. We're going to do TME, okay, is also written as just E, or total energy, and it equals our kinetic plus our potential. Our kinetic energy plus our potential equals our total mechanical energy. And so now we need to write a little something. Okay, and that's what you're going to need to write. That the total mechanical energy of a system remains constant unless acted upon by an outside force that does work on the system. So, if we start with our energy up here, then our total energy to begin with is our potential, is our mgh. If we let it roll down here, how much energy does it have?
It has 1 times mass and velocity.
Well, right, we could calculate how fast it's going because we know it's all kinetic energy, right? But the amount is equal to the amount we started with, because the total mechanical energy remains constant. So this amount of stuff down here, okay, is the amount of energy it has down here is equal to the amount of energy it has up here. So let's say the potential energy equals 10 joules. How much energy is it going to have down here? 10 joules. Now, how much potential does it have?
1/2.
No, that has no potential, right? Because our H is 0. So its kinetic energy equals 10 joules. Even if our potential energy up here equals 10 joules. Yeah? It all gets converted into kinetic. And then when it comes back up this hill, when it rolls back up again, okay, how much kinetic does it have?
0.
It has 0 kinetic, but how much potential does it have? Back to 10 joules. So it shifts back and forth between the kinetic and the potential as we go through
So
the system.
the potential always stays the same throughout the whole entire.
Well, what's our potential down here?
Oh, 0.
Potential
So
is down
it's
here.
It's opposite when they're up and when they're down.
Okay. So our potential and our kinetic, when we add them together, it stays constant. So here's my question. What if this is halfway down?
Still constant.
If this height is 1/2 h, okay, but we know that our total potential energy is 10, but it's halfway down, that means its potential here should be what?
5.
5, right? Because mgh is our potential energy. So that means it has how much kinetic energy?
0.
Vanessa? 5. Why? Because the sum remains constant. The total amount of energy remains constant. Yeah? All right, so we've got 3 things. We have kinetic energy is the energy due to motion. So if something's moving, it's going to have kinetic energy. Okay, we remember from before that potential energy is just due to its object's position. So you could have a stretched spring that has potential, but the distance of the stretch determines what its potential is. And then we have our total mechanical energy is our kinetic plus our potential, all together. So our kinetic energy plus our potential energy equals this constant, and they'll keep flowing into each other. Now, what if we did, all right, I'm going to mess up this drawing here. All right. What if we took our ball? What the heck? What just happened here? Okay. What if we start our ball down here at the bottom? How much energy does it have? Our kinetic energy equals 0 if it's not moving, and our potential energy equals 0 because it's at the bottom of the hill. Right? What would we have to do to give it some energy? We'd have to push it, right? And to give it our potential energy, you would have to get pushed back up to the top of the hill. Yeah? What is that process called? What would we be doing? We would be doing work, exerting a force over a distance, exerting energy on getting some, moving an object is doing work. So if we are doing work, if we do the work to lift this back up to the hill, now it's got potential of 10 joules, right? Because we have done work on the system. So here's the equation that you guys need to know. We have our initial kinetic energy plus our initial potential energy plus our work is going to equal our final kinetic plus our final potential. This is the value that can change how much total energy we have. And this equals total mechanical energy. Okay? All right. So that is how work and energy relate to each other. All right? And you now have enough information to finish the assignment.